Hi, everybody, and welcome to today's class. Today is actually May 11th. Today is, we're going to cover a couple of chapters again on light. First of all, the light waves and light emission. So we still have quite a few materials to cover before the end of the semester, really, before the end of the year. So we really need to get those stuff in. And so we're continuing the series on light. Let me check quickly in here. Where is your class in here? So it looks like we're on track to finish on time, okay? I think the review is not correct, the date on it, but everything else should be in good shape. You have quite a few assignments this week. So we still have, we're going to get into quantum mechanics very soon, chapters 32 and 33. And then we get into the atomic model and nucleus and radioactivity and things of this nature and relativity. And that's going to be basically the end of this topic. So we still have quite a bit of materials. A lot of heavy things are coming down the road in here, down this route in here. Okay, so let me share with you the screen. I can find it. Here it is. And let me bring this one up close in here a little. Okay. So again, as I said, we're covering a couple of topics today, namely light waves. Remember, light behaves as a particle when it comes to a phenomenon related to reflection and refraction, because there is no need. I mean, if I take a ball like this one in here, for example, and hit it on the wall, it's going to bounce back, and it's going to bounce back by the law of reflection. Actually, the angle of incidence is equal to the angle of reflection because of the conservation of momentum, and only particles have momentum. Okay, light does not. Light is a wave. It should not really have a momentum like this one in here. You need to remember this statement. I'm saying light cannot have momentum, but down the road you will see in quantum mechanics that actually it does. It behaves like particles in a sense. Okay. So that is one thing. The law of refraction goes through the different separation between two media. It slows down. So in that also I can express in terms of particles. However, light also behaves as waves. It exhibits interference behavior. And interference is only unique to waves. So light actually is a wave. Historically, the context was Mr. Newton basically took the work of people before him, including Mr. Alhazen and other people who basically work on light, including the Greeks, as a matter of fact, and he put them in a nice, basically, text, which was like what he called the corpuscular theory of light. That light is made up of tiny particles. In terms of momentum, you can clearly understand the idea of reflection and refraction. There is no problem with it. So that was the belief from the mid-1600s up to the early 1800s, where one of the phenomena that was bothersome was the phenomenon of diffraction. If I have, for example, a piece of paper like this one here, okay, and if I shine light through it from the other side, and if this is 100% opaque, for example, no light will come through this material. But if I poke a hole in here, where the light that is shining from the other end will make a perfect image of the hole, in a sense, whatever the shape that you want to make it into. So it doesn't necessarily have to be a spherical shape. So you're going to end up with basically a replica of it on the other side. It's going to be sharp for most purposes if the size is big enough. But if the size starts to become smaller and smaller, then you notice something weird, in a sense that there is a central point in here where the image looks kind of sharp, but then it starts, as you move away from that center portion, you're going to start to see the light diffusing, the light basically going into less and less intensity until it basically vanishes. So in here, there is this phenomenon of diffusion that you cannot explain it with particles. If it is a particle and goes through, it's going to impact the other, basically where you're collecting it from the other side, where you're collecting the image, and that's the end of it. But what's going on in here, it's bending on the edges and is scattering from the other side. So that can only be done by waves. Mr. Young in the early 1800s performed this experiment very well. As a matter of fact, he came up with conditions where interference can be clearly seen. In a sense, you have light shining on a surface. It's the same color, so you need at least a monochromatic beam. And then it goes through two small holes, basically called slits. The separation between the slit will determine the patterns that you're going to see in the screen on the other side. So if the separation is too wide, then you probably are going to be one side in here and the other side in there. But if the separation starts to come closer and closer, then in this case, you will see fringes of dark light and bright light on the other side. This cannot be explained by particles. This is no way that it's a particle. It has to be a wave. So Mr. Huygens came up with a principle called Huygens' principle, trying to explain this phenomenon, that, okay, light is actually a wave. As it is emitted, the wave fronts become sources for other wave fronts and so on and so forth. With this principle, we were able to understand the interference. Before the interference, we were able to understand the idea of reflection and refraction. So that's good. That made sense. Very good. And then in addition to that, we were able also to account for the wave nature of light, because those wavelets, when they interfere, they create interference phenomenon. So now there is a belief then that at that point that light is really actually a wave. Okay. So that was in the early 1800s. That was cemented by the work of Mr. Maxwell, who in toward the end of the century, around 1870 something, 76, I think, he came up with a theory that explains exactly what was waving, not just light is a wave. Because Mr. Young was able to find the wavelength and with the frequency and everything else to go with light. But there was no way to know what was waving, what was going on. I mean, a wave on a string, we can understand. A wave on the surface of water, we can understand. Sound waves, we can understand them. But what was waving for the case of light? That was the bugging issue, at least from the beginning of the 1800s toward when Mr. Maxwell came up, basically summarized the laws of electricity and magnetism, and explained exactly what was waving. What was waving was the electric field and magnetic field. All was great and beautiful until another experiments came along, and those experiments, actually, we're going to discuss them toward the next few chapters, and they throw everything out of the window. That light is not actually a wave anymore, it's actually a particle. So we went full circles, basically, as far as the story is concerned, okay? So we're going to come back to this discussion. We're going to finish it down the road. We'll talk about the particle nature of light, okay, or the duality, both of them. Again, I mentioned the diffraction phenomenon, the principle of superposition and interference. This is a fundamental principle into, look, if I have wave 1, which is a wave, and wave 2, which is a wave, if I add the two waves, it's also a wave. That's what the superposition is saying in here. You add two waves, and it really makes sense to have this, the sum as, or any linear combination being just another wave. So this is actually stemmed from the fact that the fundamental laws in here are actually linear laws. So that's what the superposition principle is coming from. Light, as I said later on, Mr. Maxwell came up with the fact that it actually, the electric field and the magnetic field are both oscillating, and that is what the wave is. What was waving. So now light then, because of the electric field, can hit your eye at a certain angle, and the electrons in your eye, in retina, start to move in response to the electric field. The magnetic field is so small that your eyes don't even notice that it's there. The intensity of the magnetic field with respect to that of the electric field is about 300 million times smaller. So usually that's why what matters really in your eye is the electric field. So what's going on in here? Then if light hits your eye in one direction, you have what is known polarization in that direction. If it hits it in another direction, light is polarized in the other direction. So the direction of the electric field dictates which way your eye responds, which you can then create. In general, light is not polarized. Light has all kinds of directions, left and right. Like, for example, in the evening when you're driving and the sun is just coming toward your eye, then because light is coming every which way, your vision is impaired a little bit. You cannot see really well when you're driving. But if you wear some of those polarizers, they can eliminate all the other lights and just keep one direction. Now, all of a sudden, you can see better. Okay, you have far more details in front of you. So that is basically what the principle of polarization is. It's very important in terms of physics, also chemistry, trying to do lab activities and things like that, trying to understand what's makes the matter and everything else. Holography, we're probably going to skip a little bit of that, and that is a perception in the brain on how images superimpose and gives you the sense of depth. Okay. There is actually a very fun problem right now in physics, and whether or not we live actually in an actual 3D, in a sense. I'll explain this one before we go any further, because we're not going to come back to it. Right now, if you look around and wherever you are right now, there is a perception that, for example, the desk has a width, length, and height. So there is a 3D image there in front of you. Now, the question in physics, is this real, or is this actually a made-up thing? In other words, is the reality really 3D, or is it just a perception that we have of it? And it's a really legitimate question. And the idea behind it is that maybe this entire universe is just the opening of we're living on the surface of a big black hole that encompasses the entire universe, which is actually a two-dimensional surface. And it's our basically day-to-day experience when we come with a measurement or observation where we make up the other dimension on the go. So it's a fascinating topic. Obviously, it sounds kind of crazy, but that's what it is. Okay. Holography is really what you're looking at right now. You're looking at your screens, for example, in me in here, and you think that there is a depth because behind me there is a chair, and behind me there is a wall with a Voyager on it and things like that. So you think that is basically how the idea behind it is. But we're not going, it's actually far more than that, in the combination of the colors basically and how they're superimposed in your brain. Then we're going to talk about what the sources of light is, namely light emission, excitation, emission spectra, incandescence, and then absorption spectra. There are three main spectra. There is the continuous spectrum, the emission spectrum, and the absorption spectrum. So those are very important in trying to do a spectral analysis of any object in the universe, whether the galaxy is far away or whether something, that substance that the person has eaten his lunch and died, and you would want to know if the person was poisoned or not. So you do either an emission or absorption spectrum, okay, knowing exactly what the continuous light need to look like. Fluorescence is another phenomenon. Phosphorescence is another phenomenon. Lamps, which are emitting all kinds of lights. And finally, which is a fun idea, it's lasers. And I have a couple of them in here. I have a green laser. So I don't want to shine it to the camera because it's really a nasty thing to have. And this is the red laser, typical laser in here. Okay. So let's get going in here. We may not be able to finish everything, but that's fine. Hopefully you guys can finish it. So again, so throw a rock on a quiet. So this is basically what a wave is, but the phenomenon in here that is that you can think of in terms of waves, they all exhibit interference. The wave fronts are those circular expanding waves in all space, in all directions. In this case, since it's a surface wave, it's going to be circular shapes. In the case of sound, it's actually spherical spheres, actually. They go all around you. If you stand, provided that the source is symmetrical, so the wave is actually going to have that spherical symmetry. So if a person stands in here, or here, or here, or there, anywhere, as long as they're at the same radius, or on top or in the bottom, it doesn't matter. If they are on a sphere, they should see the sound. So sound really is a spherical wave. Surface waves, because of their nature, they're actually circular waves. Waves on a string, they can actually have wave fronts too, but they're on a line, okay? That's what it is. So if I measure the distance between a crest and a crest, that is the wavelength. Okay, and if I'm sitting anywhere on the surface of the water, at some point, that point is going to be maximum, then it starts to go less, then it starts to go back into the normal level of the surface of the water, then a little less, then a minimum. So it's going from crest all the way to trough and anywhere in between them. okay? So what I'm saying in here is that if you wait long enough, the wave front will hit you, whichever way you want to describe it. Is the wave front the crest or the trough or anywhere in between them? That is the wave front. So what Mr. Huygens' principle is saying really is that, look, I can think of the wave as the following. Every point on the wave front, doesn't matter which one you like. Let's take the crest, okay? Every point on the crest at any time in the future, immediately there is, if you wish, becomes a source by itself for a new wave. So if I wait a second, for example, that point that is on the wavefront, this point becomes a wave by itself that creates, that spreads around it. Now, that point, the point next to it, there is another point that becomes also a source. Because between every 2 points, there is another point, so there is a middle point between them that also does the same thing. And between the middle point and any of the edges, there is another point. So think of this one as an infinite process. It's a principle. It's not something to prove, but something to visualize. Now he's saying the envelope, the cover of all of this new wavelets, he called them, is the new wavefront. Okay. So after a second, basically, the wavefront would have moved the distance in such a way that is the velocity of the wave, really. So this is the idea of the Huygens principle, and it gives me a sense from the get-go that light is a wave. Okay, and this is true actually for all waves. Okay. So again, here is a point. Take any points. These red dots in here are points on the first initial wavefront. Okay. They become sources of their own right. This is for me to imagine how the wave is moving, how the actual wave is propagating. So I can take any point in here and make it into a wave. Well, the wave that emerged from here, it's called the wavelets. It's not the entire wave. It's just a wave coming from this point. So it's going to have this much wave now. The second point will have this wave and so on and so forth, and I can build them. However, you're telling me, wait a minute. Between this point and this point, there is actually another point. Absolutely, I agree. So there is another wavefront in here. So that's, you're going to build it in here. And between this point and that point, there is another one. I agree. So there is another one. So it's really an infinite number of wavelets that emanates from the wavefront to make up the new wavefront. So the B prime is actually the new wavefront because it's a continuous, basically, cover of all of these wavelets. We drew how many? 1, 2, 3, 4, 5, 6, 7 wavelets corresponding to 7 points. But this process is really just an approximation, just to show you that actually it's not 7, it's an infinite number of wavelets in here. And then when they connect them, it's going to be this dotted line. And that is the new wavefront where it has moved actually. So this is the principle behind it. Is it right? Is it wrong? The only way you can tell if the conclusions from it are right or wrong, okay? And the conclusions are correct. So we take this as a principle. So the dot source in here created this wavelet AA prime. And if you wait, let's say, for example, it's moving with a velocity V. If you wait 1 second, this distance is actually V times 1 second. The new wavefront will be here, okay? And so on and so forth. So you're saying, what happened next? Well, next, the new wavefront becomes a source for the next wavelets. And then you make up the new wavelet, and so on and so forth. So this is Huygens' principle. And this is basically the idea behind it. Obviously, if the opening is very small in here, you can clearly see the patterns of the wavelets forming in here in the circular pattern. If the opening in here is too broad, it's because this point and this point and this point, they add up in here, and this is actual wavefront was parallel this way, and this is where the wavefront is actually parallel, at least in this region. And the only reason why you see deformations in here is because, again, the wave nature has that. It goes around the object. Now, since it's a point-like, this is basically how it behaves. Okay, again, I mentioned the diffraction before I started, and it's those colors actually that start to break around the edges of small objects. Okay, and in this case, there are so many shadows, and those shadows are actually the diffraction patterns that form. Here was an indication similar to this behavior in here that light actually is a wave, not particles of some sort, or doesn't matter what their masses were or anything like that. Okay, So this is firm confirmation. Light is a wave, okay? Down the road, I'm going to say, now this is actually confirmation. Light is a particle. So which one is it going to be? Depends on the experiment, really, okay? So now, listen, let's be clear on this. Even Newton's interpretation of the reflection and refraction, which were work done before him and including himself, that based on the particle nature of light, can be abandoned at this point in light of Mr. Huygens' principle, because even that can be explained with this principle. So light is actually a wave, okay? The only reason why we didn't see that reflection and refraction properly in there, we see it is because there is actually a buildup of waves leading to those patterns that were seen in the case of reflection and refraction. So right now, there is absolutely no reason to doubt the fact that light is a wave. This is a case for it. Okay, so this is actually an experiment to show that light is a wave. Okay, so this is why we're saying that, because of this phenomenon of diffraction, the one that we mentioned before. This is exactly what it is. So light is a wave, and it has wave fronts, and it has wavelength, and it has frequency like any other waves, like the surface waves on the surface of the water. Okay. So the amount of diffraction of wavelength of the wave compared to the size of the object, again, it bends around the big size of the object, or depending on the wavelength in here is very short compared to this big size of the object. So in here, it's going to provide you with a sharp image in here. Longer wavelength in here, big wavelength, appear to be bent on similar size objects. Shorter wavelength in here, because they appear to be broken in here. And that's the only difference between the two. It's the wavelength that determines that. So if you make the size small enough, then you're going to detect the wave nature of light. If the size is big enough, like for example, you standing in front of you're going to probably make a sharp shadow depending on the angle, of course, okay? So again, here is the point I was making earlier in here. Make the slit narrow and you will see the diffusion. Leave the slit or the window wide, and then in this case, the image is sharp, okay? The edges and everywhere else, okay? So this is, again, a confirmation that light is a wave, but it's not just that. It's actually, its wavelength is small because of this experiment. So both of them are indicating the same thing, that light is actually a wave. One of them is telling you how much wavelength you need. What is the separation between each two wave fronts? So the separation between each two wave fronts is of the order of the slit. It needs to be tiny, okay? As a matter of fact, the early experiments from Mr. Young gave numbers of the order of a fraction of a micrometer or a few hundred nanometers. So light appears to be ranging anywhere between 400 nanometer, 350 nanometer for the violet light or the blue light, all the way to about 700 nanometers, which is super long, okay? Almost a micrometer, okay? So that is the size that you need to do, or at least slightly bigger than that, for the opening in order to really see this phenomenon, okay? So limitations with focusing images in optical instruments, objects about the same size as wavelengths of light, diffraction blurs objects smaller than the wave of light, no image. For example, the atom. Can you even take a picture of the atom with light? No. The atom is of the size of an angstrom, which is about 0.5 or about 0.5 nanometer. So it's very, very tiny compared to the wavelength of light. So the wavelength of light will go completely circumventing the atom and will not even detect it, okay? So that is really the problem why we cannot take pictures of atoms with cameras. No matter how good they are not gonna be able to capture cameras. But an electron microscope might do. Because the wavelengths of an electron will be of the order of that of the atom. That's why we had some fuzzy images of the atoms. So that is an important concept in here. So limitation is avoided with an electron beam having extremely short wavelengths. So there were some pictures of iron atoms and some long chain molecules that were taken with an electronic microscope. okay, versus a regular microscope that uses light, that will never show you an atom. You cannot see an atom. When I was actually in school, in high school, and you know how some of, anyway, one of the people that was actually in the other classes, he came to me and he said, I don't believe the existence of the atom. I said, why? Because he said, there is no way we can see it under a microscope, therefore it doesn't exist. Here is the reason why you cannot see it under the microscope. I asked him actually a different question. I said, can you see your brain? He said, yeah, I mean, we saw the brain of the no. I told him, I'm not talking about a mouse or whatever, or something else, or a cat or anything like that. I'm asking about your own specific brain. Have you seen it? Well, if you didn't see your brain, I hope that you know that you still have one. Okay. So again, the point being in here is, even if you can't see something, there is some telltale signs that can only be explained by the existence of these things. Among them is the atoms. Actually, the atoms, we took some pictures of them. Okay. The emission spectrum that is coming down the road, the absorption spectrum down the road, can only be explained with the existence of the atoms. Of course, this debate now is this is high school stuff. Okay, so I know this is anyway. So features of electron microscopes use electric and magnetic fields to focus and magnify images. Better radio reception with long radio waves. So this is the features of the. So for dolphins, use shorter wavelengths, give finer details. So again, for the ultrasound, okay? So again, this is behavior for all waves. Shorter wavelength gives you far more refined images, far more refined sound. Longer wavelengths give you actually a bigger picture than the shorter wavelength. Okay. Again, I mentioned the superposition principle. If I have a wave, and if I add it to another wave, I will get a wave. However, if these two waves are actually in sync, meaning they rise together and they drop together. So in this case, it's called constructive interference in the sense that they add up so that the amplitude, let's say, for example, they have the same amplitude. They have the same height in here. If they have the same height, when they add up, they will be twice as much high. When they go to the bottom, they would be twice as deep, okay? So this is constructive interference or reinforcement. Now, when they're out of phase, meaning when one of them is max, the other one is min, and vice versa, then this is actually also an interference, but this is actually destructive interference, cancellation. Like, for example, noise cancellations for some of these devices that you have. If you know the emissions frequencies are roughly the frequency that is emitted, you can send a signal that is out of phase with that one so that it cancels whatever the amplitude is coming from the other side. In general, it can be both. It can be somewhere in between complete construction and complete destruction. So it's going to be somewhere in between them, okay? So again, if you look through this pattern carefully, you will see that there are points in here in the patterns. Of course, this is a wavefront all the way here and here. But in here, it starts to actually move around so that actually in the point in between them, it's destructive interference. Where's my pen in here quickly? So this wavefront is a peak, and it's a peak in here from both sources. And in here, they cancel. So this is destructive interference. This is a trough. This is a trough. When they meet in here, it becomes a maximum. So this is actually a constructive interference somehow. We ended up with a bigger amplitude in here. So this is basically the patterns that are unique to waves. Interference, only waves can do that. Nobody else is allowed to do that, okay? This is an exclusive job of waves. If you see anything interference, you know that, if you see interference, you know that you're dealing with a wave. That is really the point being in here. So again, this is when two waves arrive at a point and they are in sync. Then in this case, obviously, there's going to be bright. As a matter of fact, it's going to, if this is a wave, came in here, and the other wave came in here. So when you add them up, it's going to be this much wave in this point in here. As a matter of fact, it's going to be brighter than each single one of them. So if you add, this is a bright, This is bright. This is actually going to be brighter. 4 times as bright, as a matter of fact, each one. Okay, because the brightness, actually the intensity, is proportional to the square of the amplitude. So if you multiply the amplitude by 2, you're going to square the 2, and it's going to be 4 times as bright. Whereas if they come out of phase, then they will cancel each other, and this is going to be a dark area. So depending, for light, you will have a bright when there is constructive interference, followed by lack of color, or dark in this case, when you have destructive interference. So that is basically, and like the surface water, where you have a higher amplitude and a lower amplitude, and so on and so forth. So that's basically what this whole thing is. So we have constructive and destructive interference depending on which phase they come in with. What I mean by phase in here is, did they come in, both of them, in such a way that they max together, or do they in the same time and go down together, or do they come in so that when one is max, the other one is min, so when you add them up, it's going to be a single line, okay? So here is what I was talking about in here. This is actually Young's experiment. If you have a wave in here, a source in here, it's a monochromatic light. It's very important to be monochromatic, meaning the same color. So if it's a green, it's green. If it's a red, it's red. It should not be combination, because if it's a combination, they will make their own different patterns, and then there are places where it will be bright and places that, so it's going to be a mess there. So now you run them through a double slit. The separation between them is going to control how many slits you have in here, how many fringes you're going to form in the other side. Here is the trick. If you cover one of them only, what you will see something like this, a big bright area. If you decide, you know what, I don't want to cover that, you want to cover the other one, so you're going to see a different bright area. That's why I probably shifted a little bit because of the fact that you have the source is slightly above. But then, when you have them both open, like this one, you will see immediately regions of bright light followed by dark light, and so on and so forth, called fringes. So you will see dark fringes and bright fringes. Okay? The central one always is going to be bright. The middle one is always going to be bright. Then on top of it, there is a dark, and below it, there is a dark, then there is a, dark and dark, then there is a bright and bright, then dark and then bright, and so on and so forth. And you can count in here. Is this a central already? Did I count? 1, 2, 3, 4. 1, 2, 3, 4. Yeah, that's the central. Okay. So the central is always going to be bright. Here is a reason for why the central is going to be bright. Light leaving the source, they call it M in here, will travel this distance. Light leaving the source N will travel that distance. And since by symmetry, they have traveled the same distance, light will arrive in the same sync. Both of them, they will be in sync. And the central fringe always going to be bright. Now, depending on how far I move, if I move in here, this light will travel only this distance, whereas the other one travel much longer distance. If I tune my location in such a way that that difference is exactly 180 degrees, that is out of sync, completely out of sync. This will become dark fringe. Then, if I move an equal amount of distance from it, they're going to be, again, this traveled this much distance, whereas the other one traveled the other distance. In other words, the first one went a wave and then another wave before the second one joined it. The second one started when this one is actually here with two waves. So the second one will come in here with this wave. So if the separation is a full wavelength, then it's still in sync. And now you have a bright fringe. So bright fringes form when you have no difference in paths. That means they have traveled the same distance, or they have traveled distances that are separated by full wavelength. In other words, a full wavelength for the other one, then it starts the next one. When it starts the next one, the other one starts with it. So now they're in sync, okay? But if the first one travels a half wavelength, then the other one picks up. So now they're out of sync no matter how I do about it. So this one is going down, this one is going up, this one is going down, the other one. So if I add them up where they meet, I mean dark fringe. So this is the idea behind the fringes and this pattern that you see in here. Okay. So if you see this pattern at all, this is waves. If it is particles, throw a tennis ball on through this hole, it's going to land in here somewhere. Okay. Throw another tennis ball in here, it's going to land slightly above, and that's the end of it. They're not going to have 4 times tennis ball size and no tennis ball. That's going to be nonsense. If you send two tennis balls, for example, on the same side, you're not going to end up with a 4 times bigger tennis ball. It doesn't make sense. Or no tennis ball at all. So you're going to always have 2 distinguishable tennis balls. That's why this is only unique to waves. If you see this one, this is the signature of a wave. So this is a double slit experiment of Mr. Young, actually. You might read about it in the literature. And we will come down the road, we'll talk about it again. In the 1920s, it was actually redone on particles. And people now believe that there is an alternate reality because of this, based on this experiment, that we live actually in a multiverse where the reality we live in right now is one of many other choices that get split every moment of the time that is moving. Okay, so probably I've seen some sci-fi movies along these lines. Yes, no, maybe. Let me talk about another phenomenon in here, and that is the if you watch the on a rainy day, when immediately after rain, or when you wash your driveway, okay, and then there is an oil from the car or something like that on the floor. What happened to the light that is reflected? If it is only water, you're going to see probably only the white light basically coming from the sun reflecting, and that's the end of it. Okay. If you're standing next to the water, you're going to see a reflection of the tree or whatever that is in front of you. Now, if there is an oil leak, you're going to see all kinds of different colors. You see all kinds of rainbow colors in there. So what's going on in there? Here is the deal. I have 2 surfaces in here. Okay. So let's say, for example, this is oil, this is water. The oil that is going to hit the light that is going to hit the oil, and this is white light. This is not monochromatic. This is all kinds of light that are, white light is a combination of all colors. So in this case, when it emerges off of this one, it's just another white light. So just that's what allows you to see a tree or whatever you're looking at on the other side. If it goes in here and reflects off of this point in here, that is going to have another reflection coming from this point after it refracts through the oil, and then it's going to refract one more time from this point. Now here is the problem. If the light flips, depending on the indices of refraction between the 2 media, okay? If the light turns, like for example, when you take a rope and you attach it to a wall and you snatch it from one side, so it's going to happen in there, it's going to flip on the other side. So it's going to come out of sync. Then in this case, you will have destructive interference, and you will be missing some colors from the spectrum. Let's say, for example, it was white light, and all of a sudden it's missing its red. So now it's a combination of blue and green, basically, the main dominant colors in the spectrum. And the combination of blue and green is what, that indigo color, or whatever that color, that's a combination of the 2. So now that's how it looks like. Or if it's missing the blue, for example. If it's missing the blue and you have red and green that are just coming back up, then in this case, you're going to see yellow. Okay. So what the point being in here is, again, depending also on this one, it might have constructive and destructive interference. You will see all kinds of colors. You will see all kinds of colors. Here is a task for today. Can you guys reproduce this? If you have some oil and water, can you do that experiment and take some pictures? Did anybody, first of all, experience this thing before? You guys know what I'm talking about? Okay. here is what I want you to do, okay? I want you to really experiment. I know if we were in class, we would do this, okay? Actually, if you take the soap, for example, and you run it through it to make those bubbles, you will see all kinds of colors that form. And that is because of the same thing. Because the light that is hitting the bubble, it's reflecting from the outer side of the bubble, coming to your eye, and from the inner side of the bubble, it's coming back to your eye. And that combination of the two may be in sync or out of sync, depending. And some frequencies are going to be missing, and you're going to be seeing all kinds of colors. Have you done that? Have you actually played with the bubbles and have seen that or not? Did anyone of you do that?
Yeah, and on like oil.
Yeah, okay, very good. So what I'm hoping that you guys will do is try to see if you can replicate the experiment. Do not put oil on the floor, okay? If you're going to do it, you can actually try it to do it outside in the sun on a plate, for example, what you call it, a dish, for example, from the kitchen. Put some water in, put some oil on top of it, and try to go at different angles and see if you can capture some different colors that form. How is that for a task?
Sounds fun.
Okay, so hopefully you guys will take care of it, okay? So let me continue with this topic. Man, we still have a long time to go, long way to go. So again, this is exactly what I was talking about in here, okay? Air, gasoline, water, and diffraction grading is like this one. Okay, it's used. I don't know if you guys can see the colors on it or not, but it should produce some colors in here. I already see some colors that are reflected in there. And diffraction grading is actually useful to separate the lights. And this is actually a very useful device for studying spectra. Very important one to break the lights, because the lights with different colors will break at different angles. So depending on the source, it will tell me again what I have and I don't have in here. If you think of it, this is actually, let me read in here how many lines there are. This has 1,000 lines per millimeter. That means I probably should. I don't know if you can read that or not. Maybe, did I flip this thing in here? Video settings. There. Maybe now you can read it, or it's still not readable. Okay, 1,000 lines per minute. That means in every millimeter in here you have 1,000 lines. That's how light is basically broken down into this different components. We use that for an experiment in spectroscopy, actually, the topic of the next chapter here. Okay. So I'm going to skip through the questions. Hopefully you guys can go through them. Here is what I was talking about in here. Okay. Look at the different beautiful colors that form. I mean, the shape is wonderful. I mean, I don't know if I can make up this thing in here. Polarization, I mentioned the fact that light is really follows the light, I mean, the direction of the electric field. Based on that, we have light that can be polarized one way or the other. And depending on a filter, the filter will allow only a certain direction. Then that filter can be used to polarize the light that is coming off of it. If a light is polarized in one direction, remember the source has no polarization from a light bulb, for example. And when it comes out, now it's polarized in one direction. So you run it through the same polarizer, and it's still polarized in the same direction. But if you take the other polarizer and flip it back, then in this case, it's going to cancel the first one, and you will end up with completely no light whatsoever. Okay. Here is the demonstration for it. I used to have some polarizers. Now I only have some filters for colors. That's all. Okay. The thing with it is, the idea is, now you have a polarized light that emerged from the first screen, and when you run it through the second polarizer, it's going to be completely opaque. But then if you run it through a third one, man, this is a fun exercise, okay? You're going to get the light still emerge off of it. This is a good problem, actually, that we did in one of the classes, Physics 4C. The point being in here is that with 3 polarizers, you will end up with light. With 2, you don't. So that is basically because of the intensity. It's related to something called cosine squared of 5. Okay, and 5/2 actually, which is the separation between the first light. This is polarized this way, and you run it through a second polarizer, you run it through a third polarizer, and so on and so forth, and you end up with light, depending on how you orient them, you're going to end up with the with that one. But it's fun to do the experiment. I know in the lab we have some filters, and if we were in class, I would have probably done that for you guys. Okay, this is in a nutshell. Now we still have the polarization and what's going on in here. It's light going through preferential direction in here of emission transmission. And again, light emissions, which still have about, spent 45 minutes on this idea per section. So light emission is basically when an atom or a particle is excited somehow, whether through thermal agitation or by light again, or any other mechanism, and then is going to emit light. So that's basically how light is emitted to begin with. In some violent phenomenon, for example, like in the case of chemical processes or even nuclear processes, you can still emit light with different frequencies, okay? So in excitation, for example, you have an atom that receives a particle in this case. That particle will excite it. The atom now is at a higher energy level. Once it emits it, the particle actually is transmitted in this case, but now it's an excited state, so it's going to get rid of that excess energy in the form of light, and now it goes back into ground state. So this is one way of getting light out. So what's going on the microscopic level, so in the excitation, basically, on the atomic level, I should say, and the excitation, an electron, for example, jumps from a lower energy level to a higher energy level. And the higher energy level could be just the next level, or it could be actually 2 levels up or several levels up, depending on how much energy it received. So in this case, it's going to get rid of it because the atom would want to go back to its ground state by emitting light. The energy of a photon, or light in this case, is HF. We're using the word photon in here, and we really don't know what it is yet. That is actually the particle of light. Okay, so we're going to come back to it at some point. Okay, so this is how light is emitted, and it's going to be emitted with different frequencies depending on how much jump it makes back. So it goes back from, let's say, for example, in this case, we excited it to the second level, so it's going to go back into the ground state. So it's going to emit a wavelength that corresponds to this transition. Okay, again, emission spectrum is when light, this is a light source, for example, you focus the beams through a point, run it through different prisms. And the prism in this case splits the light because light, depending on the wavelength, is going to bend in different directions. So for example, I have the source going in here, I have another source coming in here, and when they bend, they will meet for constructive interference in here, but different wavelengths at different locations. So light is going to be split up. You start with white color, white light, you end up with different colors. Obviously, if you don't start with white light, but as long as it's a combination of different 2 or more frequencies, you're going to split them at the end of the day. So that's really what a spectrometer does. Spectrometer, all it does is it splits whatever source you have in there, and based on what you have in here, you can tell what emitted the light to begin with. So this is the essence of a spectral analysis. Obviously, this is an emission spectrum. There is, on the other side, an absorption spectrum, where you run light through material and see what is missing. So you know what kind of light you sent. So in this case, you know what to expect. Depending on the light that is missing that was absorbed by the material, then in this case, you're looking for all the spectral lines with the exception of some that are missing. So in this case, you call it an absorption spectrum. The absorption spectrum and the emission spectrum, they are the same, except one of them has a presence of frequencies, the other one has lack thereof of the same frequencies. So the same material can give you the emission spectrum or an absorption spectrum, the same thing, except depending on which. Here, the spectral lines depending on the material. If you see this pattern forming, you know for sure you have mercury. So it's not just one line will make a spectrum. It's not just one color will make spectrum. You have to have all of these lines with these different positions, including these 2 yellow with different wavelengths. Obviously, the first one is longer wavelengths than the second one, but they're very close from one another. This corresponds to different transitions from similarly adjusted energy levels. So let's say, for example, you have 2 energy levels very close from one another, and both of them, they will end up in a lower energy level. So this will jump in here, will give you this yellow. The other one will jump in here, but will give you the higher frequency yellow. Both of them are going to be similar colors. Whereas This red in here is actually coming from even a higher energy level. So the yellow is coming from here. Both yellows are coming from here, but the red is coming from here probably. And if you go all the way to this color in here, which is below the violet, actually in this case, it's coming from, I'm sorry, backward. I gave you the whole story. I'm sorry about that. I apologize, okay? So undo, what is that? Control Z. Let's fix this, okay? So again, let's fix that. So again, this is the yellow, the two colors of the yellow. The red is actually close by because there is only less energy in here, jump. So in this case, it's a longer wavelength. And it's actually the higher energy jump is the one that is going to give you the shorter wavelength. Okay? Did we do Control Z and fix this? Hopefully, everybody? Yes? This is shorter jumps, longer wavelength. This is higher jumps, shorter wavelength. Okay? Makes sense?
Yeah.
Very good, thank you. Cadmium in here, it has this spectrum: zinc, barium, strontium, calcium. So the fact that you found one frequency does not make sense. It does not make confirmation that you have calcium. You have to have all of them to say, now I have for sure calcium in the material. But once you have all of them, you know for 100% sure that it's there, okay? There is no ifs or buts or anything about it. That is actually calcium, signature for calcium. Okay? Its ID has been checked, rechecked, and checked again. So that is calcium. Once you have the entire, all of the lines, like this one's in here. So you can take it to the court if you like. Tell them, I know as a scientist that this material has this material in it, that the sample that you gave me has calcium in it, and this is the spectral analysis that I conducted, and this is what happened to it, and the court will believe you, okay? So these are the spectral lines of hydrogen. They're the ones actually that started the whole debate in here, and they're the ones that led us to believe that the structure of the atom has this structure actually in it. That's how we know the atom is made up in this different energy levels, because of the early studies which were done on hydrogen, and Mr. Rydberg did this analysis and came up with a mathematical pattern for it that Mr. Bohr explained it later on, okay? So again, this is the emission from what I was talking about in here. The blue light is coming from this big jump in here. Wait a minute. Don't take it as colors for a spectra or anything like that, because it looks like A is much shorter wavelength. So that should be actually the red color. And, or is it taking it to dark orange, closer to infrared? Maybe that's what they're saying. And this is red, okay? So in other words, in terms of energy, the highest is gonna be C, next is gonna be B, and the last is gonna be A, okay? In terms of frequency, this is higher frequency, this is middle frequency, and this is less frequency. In terms of wavelength, this is longer wavelength. A is longer wavelength. B is the next one in length. This C is the shortest wavelength among all of the three. When an object is under a lot of temperature, it emits radiation, okay? So this is the law with which it emits radiation, the Stefan Boltzmann radiation in here pattern. It seems like the higher the temperature, the higher the peak, but it shifts toward higher frequencies. That's why objects, when you heat them up, when you put, for example, a nail and put it on the fire, what happened in this case, initially it starts to become, it starts to become hot. Hopefully you're not touching it immediately. You have something, you have some sort of something to hold it with. And then it's going to be dark red, then red, and then it's going to be bright red, and then it's going to be yellow, and then after that, it's probably going to be start melting actually for iron. You have to be careful at this point in here. The point being in here is that it's going to be hottest when it's blue, and it's going to be coolest when it's red. It goes counter basically what we say in culture. As a matter of fact, if you do Photoshop or any of the pictures or taking cameras or anything like that, the blue is usually cool and the red is usually hot, but that is opposite to what is going on in physics. Physics is actually tells you red is cooler than blue. Okay, so popular culture is not always correct. So basically, the fact that you have different frequencies in here emitted with different wavelengths, and that is in a nutshell what the incandescence in this case is happening. Okay, I mentioned the absorption spectrum as being the opposite to an emission spectrum. So what you're doing in this case, you have, for example, a sample in here, and you're sending light on it. Okay, so the sample in this case will absorb, depending on how much energy level it has, it will absorb some of the frequencies and let go of some others. If you analyze in here what is the spectrum, you will find everything that went through is here, with the exception of some lights. Okay, so in this case, a spectrum can detect dark lines in an otherwise continuous spectrum. So the spectrum itself is everything is there. All the colors are there. Actually, it's a very beautifully colored thing. And like the first spectrum that you looked at in here, that gives you this sensation that it is all dark with the exception of lights that are present. This is an emission spectrum. In here, it's going to be the opposite. In a sense, it's going to be all colorful, with the exception of some frequencies that are missing. It's going to be the opposite. So if I take calcium and put it in here, it's going to have all the colors of the rainbow, with the exception of these colors missing. Okay, so it's a little bit harder actually to analyze, but sometimes that's the only way for you to do, because that's the only way you are interested in. For example, you have a galaxy and there is a gas in it, and you would want to know the structure of it. What kind of material does it have in it? Is it a remnant of a supernova, or is this a whatever that you would want to study in it? So you would want to study its composition. So you're going to look at it, especially if there is a star behind it. So the star will shine through it with all the spectral layers. And then all of a sudden you study the absorption spectrum of that object or that cloud, and now you determine its structure. Isn't this fascinating stuff? You can do a lot of things without even having to travel to the other edge of the galaxy or the universe for that matter, just by knowing how things work. Fluorescence is actually some of the materials that they emit light, especially under certain excitations. Again, the material is excited due to mechanical motion, and then it's going to relax by emitting the same frequencies again. This is the same phenomenon in here. If you jump from a higher energy level to a lower energy level, depending on how much jump, you're going to get a longer wavelength in this case. I mean, shorter wavelengths in this case, higher energy, so it's a blue color, and this is going to be green color again. Same idea behind it. Let's see here if we can get to the lasers before we run out of time. And here, lamps, basically the filament in here gets so hot. Remember, when an object is hot, it starts to emit. That is what the fluorescent lamps in here work, the principle behind them. Not the fluorescent, I'm sorry, the lamps, regular lamps work, okay? The neon has a similar phenomenon, except the electrons that are going through the material in here, they hit it and then they excite it, and that's how you have a light that is emitted from it. Okay. The LEDs use actually semiconducting properties for it to also get into different kinds of excitations, and that is going to emit lights too. Lasers. And I already demoed a couple of lasers for you guys. So in coherent light, many frequencies and out of phase. So basically, that's regular light. Regular light has so many frequencies in it, and each and every one of them has its own phase. So they have all kinds of patterns that form in this case, okay? You will end up with white light. Now, when you're talking about first of all, for lasers, you need really a monochromatic light. You need only a single color, like I was showing in here. One of them was a green, and the other one was a red. So this is the red color, and this is the green color, okay? So monochromatic means the same color. When it's coherent and in phase, that is actually what a laser beam is, okay? So how can we make that in the industry, okay? So lasers are a device that produces a beam of coherent light, many types and many ranges in the industry, and it cannot really be used as a weapon. Did anybody mention about the Star Wars the other day about lightsabers, or was it not this class? Was it another class?
I don't think that was here.
What?
I don't think that was us.
Okay. So it cannot work. Okay, so you try to make it, it's not going to work into a weapon. As a matter of fact, President Reagan tried to have some sort of a Star Wars project, trying to make up lasers to shoot down the enemy. It's really, you can focus energy, but not on that level, and you can use them actually in the industry to cut materials and things like that. But it's still very hard to do that. Okay. You can focus a lot of energy, especially with high frequency ones. You can really do a lot of things with them. And they are high precision devices because of the narrow bandwidth that you're going to, the narrow beam that you're going to get out of it. Okay. So how do they work? In a sample, in this case, for example, we're going to make red color. So we have a helium plus neon in the ratio of 85 to 15. So this is basically a sample of materials that you have in there. So when a voltage, in this case, zaps through the tube, in this case, it's going to excite both neon and helium. Neon will go back into its ground state with this much voltage, and helium, for the most part, also will go into its ground state, except that it has one energy level that is actually metastable. So that is going to, in a sense, stay excited a little longer than normal. So now you have helium atoms that are floating out there, some of them, and you can build up more and more of them that are actually in an excited state for a little longer time than normal. So what they do in this case, they bump into the neon atoms, and in doing so, they impart part of their energy to them. So now the helium goes back to its current state. Helium is a lot smaller atom than that of the neon. Now the neon in this case is excited. Okay, so the neon is excited, and then what happened in this case, one of them or some of them start to go back into their ground state, emitting lights in those frequencies corresponding to those transitions for the neon. In this case, it's going to be a red color, that frequency that is signature of the red color. But then what happened, you have them trapped in a region. Some of them will escape left and right, but that's fine. But the ones that are going in the same direction, you're reinforcing them with reflecting mirrors on the sides, reflecting materials on the sides. So now what you're doing in actuality in here, I'm not sharing the, so what you're doing in here, you're reinforcing this line in here, okay? It's going to come out from an atom, and it's going to excite de-excite another atom with the same frequency in the same phase. That's the whole point of a laser. Because if they're not in the same phase, then it's going to be diffused, it's not going to be focused, okay? So you need the two. It's the same frequency because it's the same transition back to the same ground state. But then, because of this reinforcement, it's going to be in the same phase. So now you have a bunch of them in the same phase moving back and forth. And the next generation will actually excite more in the same phase, in the same energy level, in the same frequency. And now you're back and forth until you have a huge beam of them. Obviously, the material in here needs to be at least to have some sort of level of transparency. And it's actually semi-transparent material. And at some point, when there is a buildup of them, they're going to start to leak. And that beam has the same frequency and the same phase. Hence, that is actually what the laser light is. So that is actually the principle behind lasers. So that is how you make lasers out of this light beams here, okay? I know, hold on, let me stop sharing. What is the stop sharing? That I'm gonna leave it to you guys. You have a couple of assignments this week, so hopefully you guys go through them. I think you have, let me check in here. You have a quiz and you have actually a homework assignment also. The homework assignment, you can work it out together, and it's not timed. And the quiz is timed, so hopefully you guys have time to go through it. And the quiz actually is from previous chapter, not from these chapters, okay? So hopefully you guys can do that, and the homework assignments, you can fix that too. Take care of that. And when we meet on, and don't forget that I'm hoping that you guys run an experiment also with light, okay? On an oil and water surface. Please don't pour oil directly on the soil, okay, or on the ground. It's really not safe. And that's it. And I will see you guys Thursday. Good.
Sounds good. Thank you.
Sounds good. Thank you.
I'll stop the recording.